Welcome to lesson 26 in Math 135. Today we're going to be in day 1 of exponential growth and decay, and we'll try to get some everyday uses of some of our exponential functions. Just like our last lesson, we got some everyday uses of some of our log functions. And what I did is I went searching for where do we use it, because as a math teacher, you know, my experience has been primarily in math, not always in those other areas. So here are a variety of places where I found that we would be using our exponential functions. Compound interest, which you've already been working with, radioactive decay. Now in the case of population growth, I'd say you have to keep that within a limited time frame. So in the next lesson we're going to look at something which I think is a nice exponential kind of growth for population. Depreciation, something that you've probably heard about, is an exponential application. Temperature change based upon the temperature within the environment. Atmospheric pressure per altitude, the rate of a chemical reaction, drug concentration in a body. There's some very interesting applications there. Then you could have possible routes in systems like internet, or in multi-level marketing schemes. So let's go ahead and get started. And since most textbooks use population models, I went ahead and decided to go with that as well, just to kind of give you some samples. And we came up with, from somewhere, a population model for Mexico. Don't know how accurate this is, but we'll work with it, okay? And A is in millions of people. It's always important to know in what units you're working. And T is how many years since 2003. Okay, so the first question that I ask as we try to use this particular exponential model is, what would the population have been in 2003? Well, since T represents your time since 2003, doesn't that mean that the T would have to be 0? So we would have, my amount is 104.9 e to the 0.017 times 0. Okay, well, I did go ahead and put the calculations up here, but they're not real hard to do, because that gives me an exponent of 0 on my e, and e to the 0 would be 1. So we have 104.9 million. Which, by the way, I really asked that question to kind of reinforce something that you see as the ongoing exponential growth model. We often use an a sub 0, and that a sub 0 is the amount at time 0. And the reason for that is because as you put the 0 in, you end up with this whole exponential value going to 1. That's why this is going to be your beginning amount. Then K is going to be some constant. It might be an interest rate, or it might be some other constant of growth or constant of decay. And then T, of course, is your time factor. All right? So this is the general equation that we use for exponential growth and decay. Now, what was the population we might have estimated for this year, this current year? Well, I don't know about for you guys, but for me, the current year right now is 2010. So that means, let's see here, T would have to be 7, right? So it's 7 years since 2003. I enter all that crud into the calculator. Hey, and by the way, it is a good idea to not do too much rounding and so forth. If you can go ahead and hang on to these digits as much as possible in your calculator, it'll give you a better answer at the end. But according to this model, in 2010, the population of Mexico should be 118.2 million. Now, I didn't go checking to see if that was accurate, but it's not a crazy answer. I can live with it. Now, we're going to use that same growth model, still for Mexico, but now I'm changing the question a little bit. In what year will Mexico double its population? Okay, double it in regards to the 2003. Well, you know what? Here's what you can think. I know I can take 2 times 104.9. If that was its population in 2003, I could double it. But I could also simply say, well, 2 times 104.9 is equal to 104.9 e to the 0.017t. Now you look at that equation, and hey, do you realize very conveniently you can divide off 104.9 off of both sides? He's gone. So we effectively have the equation, it's simplified in a hurry, 2 is equal to e to the 0.017t. Now we did practice these equations earlier, and when you have your variable sitting up in the exponent, what do you have to use in order to bring it down? We need to use logs. And since we have an e in the problem, it would make most sense to use ln. Yeah. So in fact, if we take the log of both sides, we have the natural log of 2 is equal to 0.017t, and divide that, and we get 40.8 years. Well, that might seem reasonable to you. Technically, the question said in what year. I decided that 40 years wasn't enough to double it, so I added 41 onto the 2003, and I decided to answer it as 2044. Now, I've had some students that prefer to say 2043 on that, but I'm not going to split the hairs. I think you have to go into that next year. Well, in a similar kind of problem, in what year will the population be tripled? Now let me ask you this. It took 40 years to double it. Do you think it's going to take another 40 on top of that? Probably not. Well, hey, I don't have to do much different. Do you realize all that happens is this 2 becomes a 3. So this 2 becomes a 3. It's the exact same problem, only instead of doubling, I'm tripling. And so I end up with 3's in there. And as I run that, I get about 65 years. You might be okay with that idea. Seems like a reasonable idea. In 2068, it ought to be tripled what it was in 2003. Now, of course, that's dependent upon it continuing to follow that model. Okay? Hey, and do you remember what an exponential function looks like when you graph it? Just as a quick refresher. Remember what point all of our exponential functions go through, unless you put a transformation on it. They all go through 0, 1. And then they're going to shoot up. So we're saying that that's what's going to happen to the growth. Well, do you realize that it might slow down somewhere along the way? Okay. Well, another place where we can apply our exponential functions is in the idea of half-life of radioactive elements. And I apologize to the chemistry people because it's been so long since I was in chem class, and I'm not pretending to be a chem expert. But I always think of radioactivity as that junior high classroom where all the kids are just sitting there so excited. And then as the day goes by, a few of them start to calm down just a little. And that's kind of the idea, rough idea of a radioactive element. And the half-life of plutonium-239 is 25,000 years. Now here's my everyday concept, not the chemist's way of looking at this. If I'm starting with 32 grams right now that is radioactive, I still have 32 grams at the end. I haven't lost material, but what has happened is that along the way, half of it has calmed down. Half of it has decayed into a more stable element, well, a more stable isotope of this one. So in 50,000 years, do you realize that this guy has gone through 2 half-lives? Does that seem reasonable to you? So let's see here. We started with 32. And then after 1 half-life, we're going to have 16 grams of it, half of it, that still is radioactive. Well, that's 25,000 years. Then after another half-life, half of that 16 is still going to be radioactive. That would be 8 grams. So after 50,000 years, we will have gone through 2 half-lives, and we will have 8 grams still radioactive. Well, then how much would be radioactive in 125,000 years? Now, I could do the exact same thing. I could kind of keep walking it through, you know, saying, well, another 25,000, another 25,000. But what I kind of like to do is to think, okay, 125,000 divided by 25,000, I'm going through 5 half-lives. So I'm starting out with 32, and I'm going to multiply it by a half times a half times a half. Oh, I'm going to multiply times a half 5 times. Right? Well, do you realize that I can make that problem simpler then by saying, well, that'll be 32 times 1 over 32. I will have 1 gram still radioactive. The other 31 has decayed into something that's either a 238 or, you know, some other isotope of plutonium that is going to be a little more stable. Okay? Well, that's lovely if you get those nice, beautiful numbers. But what if you are asked, okay, out of that 32 grams, how much is still radioactive in 200 years? Well, you know, I would venture to guess most of it is, right, wouldn't you? If a half-life is 25,000 years, I haven't even come close to going through 1 half-life yet. And as I ponder it, it's not a pretty number. So here's what I say. Well, I started with 32, and I'm supposed to take it times 1/2 for every half-life. But I only have a part of a half-life. So this exponent is really 225 thousandths. What? Well, that's the part of a half-life that I went through. You know, on the last guy, I took the 125,000 years and I divided him by 25,000 to find out that we'd gone through 5 half-lives. Well, in this case, it's the same idea. The numbers are just a little bit uglier. And as you run this calculation, because that's not something I'm easily going to compute in my head, we come up with 31.8 grams. And then you have to ask yourself, was 31.8 grams an acceptable answer? Yeah, because if this is only 200 years and it takes an entire 25,000 to decay half of it, yeah, that is a totally acceptable answer. Okay. Well, I don't know much about the radioactive elements. Maybe someone has determined that 10% is our target. That if we can get below 10%, we can live with that particular level of radioactivity. I don't know. It's just a proposed problem here. So let's see. If I say how long until there's only 10% of my current amount still radioactive? Well, I could play with the numbers. I'm starting with 32. But I could also say 10% of my beginning amount is going to equal my beginning amount times 1/2. And you can choose how to deal with this exponent. A lot of times I simply say raised to h. And I know what I mean h to be. H equals number of half-lives. And so then what I can do, by the way, is just go ahead and solve that and find out what h is. And then I go back and I look and I say, oh, every half-life is 25,000 years. Okay. Well, now, to solve it, do you realize the first thing we can do is divide that a naught off of both sides? So I immediately get that 10% is equal to 0.5 raised to the power of however many half-lives. Now, the other option, and I think it's probably what I did with my arithmetic here, is that you can put in here t divided by 25,000. Yeah, I just stop and think, because I always like to think of it this way. I can put it as t divided by 25,000. And that's the way a textbook formula would really run it. And you end up in the same place. Because this variable's sitting up in the exponent, what do I have to use? I have to use logs. What base? Well, you can use base 10 or base e. Why are those our limited choices? Well, that's what our calculator runs. So I can say log of 0.10 is going to equal h times log of 0.5. So the number of half-lives would be log of 0.10 divided by log of 0.5. Okay, and that'll tell you how many half-lives. Then multiply times 25,000, and we come up with a whopping 83,000 years. Now, since I don't have a calculator here to run all those numbers, I would like for you to consider, does that make sense, 83,000 years? Well, let's think about what a half-life means. After 25,000 years, how much is still radioactive? Wouldn't that be 50%? That's after 25,000. Well, then that means that after 50,000, we have half of that. Well, what's half of 50%? 25%. Okay. Well, then after another half-life, so we're up to 75,000 years, we have half of that still radioactive. Well, half of that is 12.5%. So doesn't it make sense that 10% would be a little bit more than 75,000 years? Yeah. I always like to make sure my answers make sense as I leave them. Well, you know, we also like to do radioactive carbon dating in math classes, and then I happened to come upon this information online that says, you know, there's some problems with carbon dating. Actually, I think it was a chem major that had probably tipped me off, that we don't always like to use carbon dating because there are some problems that they found with that. And they said especially for older samples, we may not get a really accurate aging of these artifacts by using carbon. You know, that they might be using, and it seems to me maybe potassium is something that they're using instead of the carbon dating. Ask your chem professors, okay? But we're going to use carbon-14 dating anyhow. And the half-life of carbon-14 is about 5,715 years. And what I'd like to do to start out with, I think it's because I'm so hard-headed. I really like to do things in a way that just kind of makes sense to me. Well, your book loves to give you formulas. Okay, so almost every college algebra textbook will give this particular formula. Now, since I'm talking to you about exponential growth and decay, and I've already mentioned this type of a formula, well, that's lovely, okay? The problem is this: how likely are you to remember this K value for carbon-14? And to me, it might be easier for me to locate, especially online, the half-life of 5,715 years than finding that K value. Of course, maybe your chem people have some great resources that you'd run right to that particular constant. But what I thought I would do is start out by showing you that you can actually do it either way. And here's what I mean. If we're going from the half-life perspective, we would have the beginning amount times 1/2, and I'll be nice and use more of the formula, the number of years divided by 5715. Now, the reason I would do that is every half-life is 5,715 years. So if I take the number of years for the age of this item and I divide it by 5715, I find out how many half-lives. Because this exponent on the 1/2 is always the number of half-lives. Okay, well then what I could do is kind of rewrite this and say, well, that's 1/2 to the 1 over 5715 raised to the t power. Now, I know you might say, why are you doing this? Well, simply to show you where that decimal comes from. And when you raise a power to a power, you multiply those exponents. So I think you might agree that those are the same. Now, what we're wanting to do is turn this equation into this equation. I'm trying to find that K value. I know what it is, but I'm showing you how it comes from this information. Well, do you realize that this guy is the very same as saying A equals A naught e to the K raised to the t? This is kind of scary, but not really. Power to a power, you multiply those exponents. Now, the reason I'm doing all of that garbage is, do you realize that this equation and this equation are totally identical, except this is replaced by this. You see, everything else is exactly the same? Well, that means that this 1/2 raised to the 1 over 5715 has to equal e to the k. And we want to find out what that K value is. Well, he's sitting up there. So what do I have to use? Logs, right? What log would be the best one to use? ln. So ln of 1/2 raised to the 1 over 5715 has to equal K. And you can bring that exponent down here in the front. And I've actually written it all up here so that maybe you can see it in a prettier print. I'm showing you how I'm getting those two equations set up to be the same. And look at that. My K value is going to equal 1 over 5715 times the natural log of 1/2, and that is exactly the decimal that they give you in almost every Algebra 2 and college algebra textbook for working with carbon dating. Okay? I just wanted you to know that it's not magical and that we don't have two different formulas. They're just different forms of the same idea. Okay, and then I said, well, how about if we do this particular problem both ways. Now, the reason for doing that, and I apologize to those of you who hate to see something in more than one way, but some of you, based upon your previous experience, might like working with this 1/2 idea. And others of you, based upon your previous experience in math and science classes, may prefer using the formula better. Okay? So I'm just trying to give you options. If you can only hang on to one, listen to one, tune me out on the other. Okay? All right, so here's what we could do. Let's see, 72% of its original carbon-14 is still found in this particular artifact, and with that information only, we want to approximate the age of this artifact. Now, if we're going to use the 1/2 idea, which is the way I have a tendency to go based upon my background, I say 0.72 times my original amount. That's how much I have now, the original amount times 0.72. That's going to be my original amount times 1/2 raised to the number of half-lives. Now, you can either put an h up there and adjust later, or you can put t divided by 5715. Your choice. Now, we actually work with these percentages quite a bit, and you notice that the a-naughts are a factor on each side, and they divide off right away, so they're gone. And I have 0.72 is equal to, I could write that as a 0.5, raised to the t over 5715 power. Because that's up in the exponent, I need to use logs. Hey, do I really need to go to ln's at this point? No, I can, because it's on my calculator. I choose either use ln or use log base 10, whichever you prefer. I'll just go ahead and write it as an log in this case, base 10. And that exponent will be able to come down. You might multiply both sides by 5715 times the log of 0.72 equals t times the log of 0.5, and then divide. T is going to equal whatever this monstrosity calculates to be. Okay, and I'm pretty sure I ran it. Let's see if that's going to pop up here. Oh, I did the other one first. So, oh no, I did 2709. I used ln, that's why I didn't notice it right away. I used natural log because I'm lazy. Instead of writing 3 letters, I write 2 letters. I know, that's bad. But I get 2709 years. Now, when I run the other equation, a equals a naught e to the negative 0.000121 t. And I say 0.72 a naught equals a naught times e to this ugly exponent. The a naughts cancel out, and I want to use natural logs, right? This time I really want to use the natural logs because of the e. So natural log of 0.72 is equal to negative 0.000121 t, and then just divide. Now you can see that's actually an easier calculation, you know. If you're comfortable and if you're going to remember that, go for it. And when you do that, you get 2715. Well, you know, if you're going to round, that's 2,700 years. So you could say, yeah, it's about 3,000 years old. I'm okay with that. But I also asked the question, which one do you think might be a little bit more accurate? Of course, I realize that's a little bit of an unfair question. But I simply wanted to point out that when we found this decimal, we actually rounded him off. So in my mind, this particular answer might be a little bit more accurate. Of course, in both cases, I'm using the 5,715 years, which is a rounded off situation. But because this decimal was rounded off, I actually think if you want, maybe using the 1/2 is slightly more accurate. But the chemists are totally okay with this other guy. Okay? Well, we're going to go back to some population growth. And in this case, I've totally set the problem up a little differently for you. You could go to the Census Bureau and you could find out that in 1990, Texas had a population of about 17 million. And then the 2000 census has them at about 21 million. Now, here's where the math book fake problem stuff comes out. If this rate of growth is sustained, and we want to use an exponential model for this, what would you estimate the population to be in this census? Since we're all excited about our current census going on here. Well, let's see if we can set this up. Do you think I'm going to use a 1/2 in this case? No, we used a 1/2 in that last one because we were repeatedly multiplying by a 1/2. So you say, well, how would I even get started on this? Well, the key is that if you think that this is going to be an exponential growth model, then you're going to use A equals A naught E to the KT. By the way, we can technically use any base here we like. You could use a base 2. You could use a base 10. 10 would make more sense than 2 because of our calculators. However, it simply means that you've got to maybe provide some information along the way. If you're going to give an equation, make sure they know you use some weird base. A lot of times we are using the E, okay? But it wouldn't have to be E. So here's what I could say. How about if we use that 17 million as our beginning population? Now I know you might say, wait a minute, nutty lady. Texas didn't begin in 1990. I know, I was alive by then. But we can use that as a beginning time. Because time is a relative thing, so you can kind of set, boom, here's where we're going to start. It's like when you hit that button on your stopwatch, okay? So we're going to use 1990 as our beginning time. So in 1990, our amount was 17 million. I don't want to write all those zeros, so it'll be understood that my amount is in millions. And then we had an amount of 21 million later on. How much later? Well, from 1990 to 2000, so my time was 10 years. And I don't know that K value. You know, the K value for carbon dating was that negative 0.000121. Well, for each element or for each problem of exponential growth, that K value is going to be inherently connected to that problem. Okay? But you notice that's the only unknown, so I can find it. I can say, well, 21 divided by 17 will equal e to the 10k. Because I have e, let's use natural logs. So natural log of 21 over 17 will equal 10k, and k will equal natural log of 21 over 17 divided by 10. Okay? And I think I put the decimal here because that's not something I'm going to do in my head. And we came out with a 0.021. Well, are you okay with that being positive? You know, the last K value is negative. Why was the last K value negative and this guy's positive? Oh, because the population of Texas is growing. The amount of radioactive element was decaying or declining. That's the difference. Okay, so it kind of helps to be thinking about the whole problem. A positive K value is expected in this particular case. So now I know that for Texas, A is equal to beginning amount times E raised to the 0.021 t. Well, and I actually know this beginning amount as well, don't I? I can say A is equal to, the beginning amount was 17. And something you'd have to note, my amount here is going to be in millions. My time is number of years since 1990. Remember, 1990 was when we decided to start it all. That was our beginning point. Okay. So that means that to find the population in 2010, well, then my t value is what? 1990 up to 2010. Oh, it's 20 years, right? And again, I'm not going to run those calculations. There we go, 25.87. So you guys can go check that. Of course, we're just now collecting that census data, so I couldn't even tell you if I was willing to go look for it, see if this worked or not. Now, the problem works. It's just a matter of, was this a good model for Texas's population? So let's recap what we've done here with some exponential growth and decay, and we'll be spending some more time looking at some other types of population growth in the next lesson. We do have some real special exponential growth problems, the half-life, and if you like, you can use your common sense and approach those from that perspective. Okay, that's a possibility. And you can always use this basic formula. And sometimes we like R and sometimes we like K. In both cases, that R value is going to be your growth rate or your growth factor. And of course, if he's negative, it's declining instead of increasing. Okay? And certainly use logarithms as you need to in order to solve these problems, because lots of times you will end up with your unknown sitting up in that exponent, and you know you need the logs to pull that down. Okay, well, I hope you have fun doing that, and of course you might want to email me if you want to give me some better info on carbon dating or on radioactive half-lives. Okay? Have a great time. See ya.